Most people want a clean, fair and sustainable world, and it is frustrating that's not happening sooner. Political indifference or vested interests do contribute to this, but there's also a host of technical problems that have to be solved before we can reach this green future. We can't overhaul the entire world without overcoming some obstacles along the way. My name is Cormac O'Malley. I'm an electrical engineering PhD student with a research focus on low carbon power system operation. And I want to delve into these problems with you and hear from experts about the solutions that research can offer.
From the Integrated Development of Low Carbon Energy Systems programme at Imperial College London, this is Low Carbon Conversations, a podcast on the challenges of building a decarbonised energy system and the research that's helping us to overcome them. This podcast is supported by Energy Futures Lab, Imperial's Energy Institute. For more information, visit imperial.ac.uk/Energy Futures Lab.
In this episode, the UK has set its sights on being net carbon neutral by 2050. And to achieve this, we need large-scale electrification of our energy systems, including heating and transport. But doing this is pointless if we're not generating the electricity itself from low-carbon and renewable sources. There's multiple types of renewable resource, like wind or solar, but which of these are more important in our future generation mix? Is there a place for nuclear plants alongside them? And what consideration do we need to give emerging technologies like grid batteries or carbon capture and storage? My guest today is Dr Marko Aunedi, who is a research fellow at Imperial College London, and with almost 20 years of experience in energy system modelling, he's the perfect guest to talk about some of these issues. His expertise covers system integration of renewables and electrification of heat and transport, as well as assessing the system benefits of smart grid solutions, energy storage and flexible demand. His research has informed the energy industry, government and regulatory bodies about the role and value of emerging new technologies in supporting cost-effective decarbonisation. I found our conversation very informative and enjoyable, and I began it by asking Marko what is entailed by the term generation mix and why the year 2050 is particularly significant for the UK.
So the generation mix is a portfolio of technologies that we use to produce electricity. So the electricity that everyone uses. Traditionally, especially in the UK, electricity has been produced using a mix of thermal generation, such as coal, or more recently gas, as well as some other generation technologies such as nuclear. But more recently, we've been having more and more renewable technologies thrown into the mix, and this has all been motivated by the objective to decarbonize electricity generation. So we want to have electricity generation with as little carbon footprint as possible, and of course things like wind and solar PV generation, they can generate electricity without any carbon footprint, unlike things like coal and gas, where you have to burn a certain amount of fuel, and when you burn that, you emit CO2 into the atmosphere. The UK, as a country, has declared it wants to be carbon neutral, or I should even say greenhouse gas neutral by 2050, which means the entire UK economy needs to be a net zero emitter of greenhouse gases. And of course, carbon dioxide is the most the predominant source of greenhouse gas emissions. So what does that mean for the electricity supply? So electricity supply is seen as one of the sectors of the economy which is probably easier to decarbonize than some other ones. So things like aviation, shipping, agriculture are seen as more difficult because it's more difficult to substitute, let's say, jet fuel with something which is zero carbon, whereas it's more easy and it's getting more and more cheap to replace gas electricity generation with renewable electricity generation. So therefore, our let's say objective or our thinking is we'd like our electricity system to become at least entirely carbon neutral, which means that we don't want to emit any carbon from the electricity system. while still meeting all the demand. There is thinking that this should go even further, so that the electricity system should actually be a net negative emitter to compensate for all those difficult sectors outside the electricity that will maybe still have to emit some carbon or some greenhouse gases, so that the overall economy hits its net zero target by 2050. And as you probably know, UK has actually legislated hitting the net zero greenhouse gas emissions by 2050.
The goal is to get our entire economy to net zero by 2050, including transport, heating, electricity. And you're saying that what's likely to happen is to get that sort of holistic decarbonisation, our power sector is likely to have to actually be a carbon sink. So it has negative carbon emissions in order to offset the more difficult to decarbonise sectors. I'm curious how you can have a negative emission power sector.
Yeah, it sounds like a very odd concept, fully admit, looking at how power systems traditionally have been set up. So yeah, the thing is, so we would like to have a technology that allows us to capture more carbon than we emit from the electricity system. So these technologies are not quite there at the moment, but they are being developed. So there are several groups of technologies. So there's something called the carbon capture and storage, which is essentially a piece of technology that you fit onto a thermal generation plant, so that you extract CO2 from its flue gases. So imagine a big plant with a big chimney, essentially, and then all the carbon that gets out of that chimney stack, you capture, and then you can pump it underground, so that you avoid having to release it into the atmosphere. So you can fit that sort of technology onto a coal generator, onto a gas generator, or even onto a biomass generator. So if you imagine a biomass generator which uses, let's say this is a zero carbon fuel, and then you also capture the CO2 that you release when you burn that fuel, then your net effect is negative.
So this technology, when you attach it to a fossil fuel plant, will make that plant carbon neutral. But if you attach it to a thermal plant that burns farmed trees, you're capturing CO2 from the air into wood, you're burning that wood, and then from the flue gases, capturing that CO2 and putting it underground. So you're moving CO2 from the air to the ground, so you actually have a carbon negative technology that also produces energy.
That's correct, yes. There are other things such as direct air capture, or DAC, which is a mix of thermochemical technologies which actually absorb CO2 directly from air. Now, absorbing CO2 from air is a lot more difficult, because there is less than 1% of CO2 in air. It's mostly nitrogen and oxygen. So it's a more difficult job to do than the CCS, which captures CO2 from the flue gas, which is almost entirely CO2. But there are these technologies. They are becoming cheaper, and they're also an option if you want to have a net zero or net negative carbon system. These technologies, of course, cost. You need to spend money to build them, and it also costs to run them, because they are a net user of energy. So you might need to produce more electricity to drive this carbon air capture. But it might be worth it if this is where we want to get to by 2050.
You have a complex mathematical model that looks at all levels of the power system, including investment and operational costs. You use this model to find the cheapest generation mix to meet the energy needs of the 2050 system whilst ensuring carbon neutrality. In this podcast, we're going to talk about what that optimal 2050 generation mix is. And then at the end, we're going to talk about some obstacles that need to be overcome before we can reach this generation mix. But before we get on to defining what this optimal generation mix is, what generation mix is optimal is highly dependent on the energy needs it is meeting. So I thought it'd be useful if you could go over the expected differences in energy demand in the UK between now and 2050.
Yes, absolutely. So what we see from our modeling results, I mean, what the modeling suggests is that our system in 2050 will look completely different to what it looks like today. So there'll be a fundamental change and transformation, because we will eventually have to get rid of all the traditional carbon emitting generation. So all of these gas turbines, all of the coal units, they will just have to close down. And on the other hand, we would also like to decarbonize our heating and transport. So the way we heat our homes and the way we drive our cars. So you can imagine that a lot more of the heat for the residential sector, for the households, will be provided through things like heat pumps. And of course, a lot more people will have to drive electric vehicles, which means we'll have to meet an even higher electricity demand in the future than what we do today.
Heat usually flows from a hot place to a cold place, and according to the second law of thermodynamics, you have to put in energy to move heat from a cold place back to a hot place, sort of like pumping water uphill. Heat pumps do this to heat your house. They move thermal energy from the cold outside into the warm inside of your house. Very similar to how a fridge works, where it moves heat energy from the inside of the cold fridge to the outside of the fridge, which is in your warm house. But in that case, the useful part is the cold inside, and in a heat pump's case, the useful part is the warm section. Recently, there has been a lot of interest in heat pumps as a potential way of decarbonising domestic heating. They are electric, so can potentially run on low carbon generation sources like renewables. They're more efficient than simply using electricity to heat up elements within your home, because for each unit of electrical energy you put into a heat pump, you get some multiple of that back in heat. However, because the UK uses about 5 times more energy heating our homes than we do on supplying them with electricity, electrifying our heating puts a lot more load on the electricity system, and so is something that we need to consider alongside electrification of transport when considering what the optimal generation mix will be in 2050. So maybe you could lay out what this optimal generation mix in 2050 really looks like.
Yes. So with renewables, actually, in a similar way to the traditional fuels, a lot of it is about how much natural resource you actually have in a certain location, in a certain country. So the answer to what's the best net zero carbon portfolio will be a lot different in the UK than, for instance, in places like Greece. So the UK is quite blessed in terms of abundant wind resource, and that especially applies to the offshore wind. On the other hand, the cost of building offshore wind turbines has gone down dramatically over the past 5 or 10 years. And when I say dramatically, I mean something by the factor of 3. So that means that the best thing UK should do for 2050 is to build a large amount of offshore wind, which will become a lot cheaper. And what we also see, because wind is volatile, is what's often called intermittent in output, which means sometimes it does blow, sometimes it doesn't, but you still want to have your electricity. What we see as particularly useful is to couple that high proportion of wind generation with some energy storage. And at the moment, the cheapest energy storage that seems to be around and will be around for the next few decades is battery storage. So that will allow us to use all that wind resource, but also to store that energy for when we actually need it, so that we don't have to produce exactly how much we need at exactly each point in time.
So what you're really saying is that the main changes are we're going to have a lot more wind and a lot more batteries. I thought it'd be useful to really talk about why those two come together. Is it as simple as if your demand is doing one thing and you have more wind, you charge the batteries, and then if you have less wind than the demand, you discharge the batteries? Is that their only use, or do the batteries offer other advantages to the system outside of that simple energy balance?
There are other advantages as well. So by all means, at the macro scale, being able to absorb excess wind generation and then release it later when, for instance, demand is higher but wind output is lower, will be one of their key advantages. But batteries can also do other things, so they can allow you to retire some of your thermal generation because they can provide firm capacity backup for wind. What they can also do is that they can avoid network reinforcement. So if your batteries are placed in a strategic positions across your distribution network, then even if you have a high demand on the distribution network, if you manage your batteries carefully, you might avoid having to reinforce that network, so building thicker cables and wires to supply your demand. So batteries can capture several sources of value.
Okay, so we have wind and batteries. Is solar likely to be a major component of the UK system?
The answer is probably not. I mean, we will have some solar, and you already have quite a lot of solar in the UK, but the availability of the resource, of the energy resource for wind and for solar is just vastly different in a geographical location of the UK. As an illustration, to throw a few numbers in, if you build a unit of offshore wind capacity, then it will typically operate around 55% of the time during a typical year. Right, so you have 55%. If you build the same amount of solar PV capacity, and even if you put it at the best possible location at the south of UK, it will operate roughly 11% of the time of the year. So there's a 5-time difference between how much energy you can get from one unit of capacity. And that inevitably tilts the balance quite strongly in the favor of wind compared to solar. But if you move to another country, like as I mentioned, Greece, Spain, or some country, with more southern latitude, the story shifts around. So that you get a lot more utilization of your PV capacity, and typically the utilization of wind is a lot lower. So the answer would be a lot different if you looked at a different system. But for the UK case, with the current cost information we have, it seems that wind is a clear winner.
Yeah, it's a massive shame you can't generate electricity via rain or clouds, because then the UK would be doing quite well.
Well, in a way, wind is related to those very, how would I say, variable changing patterns. So
That's
there
a
you
scientific
go.
way of putting it.
Some. Yeah.
Right. So the other big decarbonisation technology that I think most people will be familiar with is nuclear generation. Where do you see nuclear in our future?
Yeah, that's a very good question, and it's also quite prominent in the whole decarbonisation debate. So nuclear is obviously a zero carbon technology, but it's got completely different both technical and economic properties to wind and PV. So first of all, nuclear projects are typically very big, and they typically are built for a long period of time. So you have a typical period of around 10 years from kind of starting to design and apply for permits to build a nuclear until that project is actually built and operational. So there's a large lag time. The other thing which doesn't work in nuclear favor is the cost. So you might be aware that there's a nuclear plant being built at the moment, Hinkley Point C. It's probably going to get operational in the late 2020s. The cost of a unit of energy that the government has promised to pay to that plant is roughly double or slightly more than double the cost that the new cheaper offshore wind plants are getting. So any new nuclear capacity that would be built in the UK would have to be a lot cheaper than that Hinkley Point C plant. We did some sensitivity analysis on in which case would nuclear actually start to become an attractive option, to be a part of that net zero carbon portfolio. And it seems that it would have to get a lot cheaper than it is today. So from something which is around the £90 per megawatt hour, which is what Hinkley Point C is getting, it would have to get down to at least 60, and ideally to something like £45 per megawatt hour. So roughly half the price that at which nuclear plants are being built today.
I guess my final question on which type of renewables will be in this mix is why the focus in the UK seems to be so much on offshore wind. Onshore wind, in some things I've seen, is actually cheaper, and I'm just curious why offshore is the one that's talked about so much. And then as a follow up to that, you say that the UK is blessed with really good wind resources. Is that purely because we have a very windy sea that's very shallow, or are there other reasons? And do we have such a good resource here that we could potentially sell our energy, make so much energy that we can then sell it to the rest of the world? So be an energy exporter, really capitalizing on this resource that we have.
Yes, that is a good question, and we definitely see that there is a potential for the UK to use its competitive advantage in terms of the abundance of its wind resource. To come back to your question of onshore versus offshore, onshore wind was, let's say, the capacity that was built in the first wave of wind expansion in the UK, and most of it was built in Scotland, so the very north of Britain, because that's where the best locations were. And of course, it was a lot cheaper to build on land than to build offshore wind turbines. Now, in the meantime, the game has changed a lot. So quite a lot of wind onshore has already been built. There's been more and more resistance to developing further schemes, so resistance from local communities. At the same time, the cost of offshore wind has gone down a lot. So a lot of new technologies have been developed, and technologies have been improved and made cheaper. So technologies for building, technologies for connecting them to mainland. There's also something that's to do with the economies of scale. So the wind turbine developers just developed turbines that were big enough to capture a lot more of the wind than what was previously the case. So with all of these technological developments, offshore wind has suddenly started to become a much more interesting prospect. Also, offshore wind doesn't suffer so much from, let's say, the resource constraints that onshore wind has, because you can't just build onshore wind wherever you want. There are lots of restrictions, some protected areas like national parks. So yes, offshore wind can be built in large swathes of the UK waters, and so the latest estimates I've seen are that we have at least 100 gigawatts of offshore wind resource to be developed in the UK, but it's probably going to be even more.
Okay, so we've set out what that optimum generation portfolio looks like, but this podcast is a podcast on overcoming obstacles to a green future. And you've just given me the solution, haven't you? I was wondering, what challenges do you see in getting to this optimal portfolio? What are the obstacles we have to overcome to get there?
Well, yes, it's correct. It's not going to be easy to come from where we are today to this lovely endpoint in 2050. So in analysis, we focused on what the system should look like in 2050. We didn't so much look at the trajectory of how we come from where we are today to where we want to be in 2050. And it's quite obvious that there's a huge number of challenges in terms of building that future system. So, for instance, we foresee that the capacity of battery storage will increase something like 100 or 200 times from what we have today. So obviously, that sort of change will require capacity increase in the global supply chain of battery storage. So you probably couldn't deliver so much battery storage using today's manufacturing capacity. So there's an implicit assumption that this capacity will need to go up in order to satisfy this global demand for battery storage. So that's something that will need to be resolved. And similar for offshore wind, the build rate that we've seen historically are a lot lower than what they should be over the next few decades. So again, there's an expectation that the supply chains will match the increased demand for these technologies and allow us to hit those targets. Because if you can't build enough of those technologies, you'll have to substitute them with some other technologies which might not be as cost efficient. So the overall solution will potentially be a bit more expensive than it should be.
In this analysis, are you relying on any sort of subsidy or government policy apart from the legislated 2050 net zero? Are you relying on any tax cuts, those sort of things that could make this final number very difficult to reach if they were removed?
Ideally, this should be carried out by the market. And I should say that in our analysis, we do not consider any tax cuts or subsidies or any sort of incentive mechanisms. So the analysis is purely cost-based, purely based on the economic cost of these different technologies, but imposing this carbon constraint of being net zero in 2050. I think looking at where the cost of these technologies are going, that there'll be less and less need for subsidies. And there's been actually a recent paper by a colleague from Imperial in Nature Energy, which is arguing that essentially we are already seeing a subsidy-free offshore wind emerging across several markets, especially around the North Sea. So I think you might expect that going forward, you will need less and less and eventually complete zero subsidies to make these happen. But that doesn't mean, of course, that we already have in place efficient and perfect market mechanisms which will actually deliver these net zero outcomes at the lowest possible costs. I think there's probably still more to be done to ensure that we do get these efficient outcomes through market mechanisms. And I guess that's something that will need some work over the next couple of decades.
Okay, great. We don't have to rely on the government then. Marko, there's actually two bonus questions at the end, which I'm going to ask you now. So,
okay.
What machine or technology that is in development or very early development do you think would most speed up the energy transition if it worked well and became available now?
Ooh, that's a tough one. If you had a really cheap way of producing hydrogen, then you could use hydrogen as this intermediate vector, which could link electricity, heat, potentially even transport. The issue is, however, that technologies that are used to produce hydrogen, such as electrolyzers, are still quite expensive to build. So that, in a way, limits the role and usability of hydrogen as this intermediate energy carrier. If that somehow it now becomes a lot cheaper, that could change configuration of our net zero carbon system significantly, potentially. It could also mean that, for instance, you don't want to decarbonize road transport purely by electric vehicles, but you might also want to do something with hydrogen, such as hydrogen fuel cell vehicles. So you might need to have like a mix of these technologies. And similar for heating. So if your heating is not fully electrified, but you also use some hydrogen in your boilers to provide, let's say, heating during the very coldest periods, then that might actually be the best solution overall, the best trade-off across different vectors. But yeah, at the moment, this is still a fairly high cost technology.
Oh, I quite like that. I've never considered hydrogen in a pipe as a direct equivalent and sort of supplementary to electrons in a wire, having those sort of two energy vectors that we can change into sort of transport heat energy. I quite like that comparison, and I think that does kind of highlight why it might be useful in the future, but I understand it's a long way off. The second bonus question is to do with the fact that climate change is an ecological tragedy. It's unfortunately likely to lead to many animal extinctions and ecosystem loss. If you could de-extinct any animal that is currently extinct, you don't have to have any good sort of charitable reasons for this, just because you think it would be cool. Which animal would you choose?
Okay, I've got kids, so I'll have to go for a dinosaur. And because I want to make it as scary as possible, it just have to be a T-Rex. Sorry.
Yeah, that's yeah. I mean, I think that's kind of the probably the most standard answer. Everyone wants to see a T-Rex. Great. Thank you so much for coming on. I learned a lot.
Thank you, Mac, for the opportunity.
Thanks for listening to Low Carbon Conversations, a podcast from the IDLES programme at Imperial College London. If you'd like to get in touch, email us at idles@imperial.ac.uk. For more information about energy research at the college, or to learn about our internationally unique Master's programme in Sustainable Energy Futures, visit imperial.ac.uk/Energy Futures Lab.